Hi everybody, and welcome back to the Hanson Math YouTube channel. Today's lesson will be part 2 on Introduction to Limits. Part 1 was a Desmos activity where you got to see the difference between having a defined function value as x is on a certain value versus how the limit is the value as x approaches the number from both sides, but doesn't necessarily get to it. So speaking of that, let's review the definition here, that if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, and that becomes important, the limit of the function as x approaches c is L, written as the limit as x approaches c of f of x equals L. So if we look at this scenario here, it says, what is the limit of the function as x approaches 3? So here is our 3 on the x-axis. And as we follow the curve from the left side and we get close to 3, we're right about here. And as we trace the curve on the right side, we're also at the same height. So you're converging on the same height of 5, which is precisely why the limit for this function as x approaches 3 would just be 5. Okay? And you did see that on the Desmos activity. Now, a good counterpoint to that is the second graph over here, where we have what is the limit of the function as x approaches 3. So if we follow the left branch from the left and we get towards the x-coordinate of 3, we're up here at a height of 5. But as we approach from the as we approach from the right side heading left, the function hits a value of 2. So that's a contradiction. Even though this point here is defined when x equals 3, y equals 2, because it's solid, it's defined, the limit does not exist because it does not approach a unique number, okay? There's this disconnect here. When you approach from the left, you're at 5, but when you approach from the right, you're at 2, okay? I hope that makes sense. So for this one, even though it's defined as a function at x equals 3, the limit does not exist because it doesn't converge on a single value from both sides. Okay, next we're going to look at 5 different scenarios, and to do that, I'm going to switch over to Desmos. You could use TI-83, TI-84, but I think just due to how Desmos is much more flexible with zooming in and zooming out and whatnot, I think that you'll be able to get through this assignment a lot more quickly on Desmos. The caveat is with the graphing calculator, you can have that in your hand while you watch the video. So for this one, you might want to print my supplied PDF file, or you might want to write down these 5 problems on a sheet of paper. But I'm going to do them one scenario at a time, starting on Desmos right now. Okay, so I queued up desmos.com. I'm going to click the red button, Start Graphing. And I'm going to put in scenario 1, example 1, which is f of x equals x over, to do square root, I'm going to press SQRT, and it comes up, x plus 1 inside the square root. To get out of the square root, I hit the right arrow, and then I put my minus 1, so it looks correct. Now, your worksheet says, example 1, the function value is not defined, but yet the limit does exist. So it says the limit as x approaches 0. So as x approaches 0, I'm clicking on the red curve with my mouse or my cursor, my trackpad, and I move the x coordinate to 0, and I see it says undefined. Well, that makes sense, because if I were to plug a 0 into the denominator here, I would have 0 plus 1 which is 1. The square root of 1 is 1. 1 minus 1 is 0. And as you know, when you have a 0 in the denominator, the function is undefined. So it makes perfect sense if I plug in a 0, the y-coordinate is undefined. But this is different than a limit. The limit, as you approach x equals 0, you're approaching a height of 2 from the left side and from the right side. So even though there is no defined value at 2, at x equals 0, excuse me, the limit is still 2. Again, this illustrates the point that the limit is different than the function value. The limit is just the value that you approach. It's not necessarily that exact number of the function. Okay, so we're right here. We're hovering at a height of 2 from both sides. So on your paper, you will write down that for example 1, where the function value is not defined but the limit does exist, that the limit equals 2. All right, we'll move on now to example 2. Example 2 says the limit as x approaches 0 of the numerator is 2 to the power of x. So that's 2. To do a power, it's easy to do caret, which is shift 6. Shift 6 to the power of x. And the denominator is just x. Let's see what that looks like. Okay, now the beauty of Desmos is you can zoom out, you can zoom in, and if you get kind of screwed up, too far zoomed out, if you click this house over here, it goes back to kind of a normal view. So example 2 says comparing left and right behavior. So it says as x approaches 0. So we can see here, if I get out my pen, if we approach 0, so if we follow the curve this way, it takes us down and it appears forever. And if we take this branch and we start heading towards an x value of 0, it takes us up forever. So you're going infinitely high and infinitely low. That there is a contradiction. So on this one also, the limit does not exist. Okay, there's no convergence on a single value. Okay, that was example 2. All right, example 3 is the limit as x approaches -1 of the function. We have a 1 at the top of the function, the numerator, and the denominator is x squared plus 2x plus 1. Okay, and the directions say what happens here as, what's the limit as x approaches -1. Okay, so -1 is right here, and if you look, the graph goes infinitely high. It's not converging on a particular y value. If we zoom out, it appears, and again, my arrow moved, it doesn't, the function doesn't stop. The red line goes up forever. So since it goes to infinity, it doesn't converge on a value. So again, on this one, you will also say that the limit does not exist, DNE for does not exist. Okay, it does not converge on a single particular y value. Okay, that was called unbounded behavior. It just goes on forever. That was example 3. All right, example 4 says we have the numerator is, I'm going to put it in parentheses since it's a numerator, x to the power of 3 plus 2x plus 1. Backslash to get my fraction, and here I need 4x cubed minus 2x squared plus 9. Okay, what does this one look like now? Notice how zoomed out I am. I'm going to hit the house, and it looks something like this. Now, this one says, what is the limit as x approaches infinity? It says, what is the limit as x approaches infinity? So positive infinity means you look to the right on the x-axis. So I'm going to look here, and you might think that this red line of the function is going to go lower and lower and lower and approach a height of 0, which it can be, an answer of 0 where it gets infinitely close to the x-axis is an asymptote. 0 is often the limit, but on this one you'll notice if we keep scanning and scanning, this is why Desmos is so nice. And I go minus, 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 zoom out. I click on my red line and trace. Ooh, I was at like 0.255, now I'm at 0.251. I'm going to guess that the limit on this one is a quarter, 0.25. So I'm going to say the limit is a quarter. And in a future lesson, we're actually going to break down the numerator and denominator, and we're going to see arithmetically if we can get this limit of a quarter. But for now, I just want you to use the graph and trace on Desmos. Okay, so this one has a limit. The height of the graph does settle on 0.25 or 1/4. It settles on that one value. It's not going to infinity or bouncing all over the place. And again, just to be clear, you're looking at the y-coordinate as x approaches infinity, just going on bigger and bigger and bigger. Okay, finally, that will take us to the fifth and final example, which is called oscillating behavior. This is kind of a fun one. So this one is simply going to be looking at as x approaches negative infinity, which means to the left forever, x cosine x. Woo! Okay, what does that look like? Holy cow. If we zoom out, it looks pretty groovy, huh? I don't know, it looks like a radio, reminds me of a radio station. So if you follow this one, negative infinity, which means to the left, you'll note that as you go this way forever, that it oscillates, right? It goes up, down, up, down. It doesn't converge on a single number. So by definition, the limit does not exist. So for this one, the limit does not exist. We call this an oscillating function where it doesn't settle on a particular y value. It just jumps up and down forever. So the limit does not exist. Cool. Okay, so if you've made it this far, we just went through these 5 examples as notes together on Desmos. Now I'd like you to continue with Desmos and do this page, which is Precalculus assignment number 12. And this is like a throwback to what you did on lesson 1, looking at the table. Be particularly careful with letter C. And then you're going to throw all these into Desmos. Pay attention to the limit value on the x that you're looking for and tell me what would be the limit. Again, it could be a numeric number, it could be 0, it could be does not exist. And when you get to the last block of problems, which is number 3, use Desmos or your TI-84, which I don't recommend. I do recommend Desmos. If the limit does not exist for any of these last A, B, C, and D, briefly explain why. You could use some of the language I used in the examples. So there you go. I hope you enjoyed this quick lesson on limits as we march closer and closer to the idea of calculus. Thank you very much for watching my video and have a great day.